The dog.
Oh. Yeah.
This one's specifically for Oliver.
Yeah. I get that one.
Yeah, that one's
It doesn't
funny.
have to be a student. When a classmate tells you that they did show their work, their work is just the final step. Like, what? What intermediates went through your head in half a second?
I mean, it's great when it works out, but then when it doesn't work out, then it...
Oh, the funny thing is, on the circuit for Lopez Wallace rule, they misspelled it like twice. Or it was misspelled like twice.
Yeah, I saw that, and I'm not sure if you can spell it both ways or if it was a typo.
I don't know.
I always liked that one, but it's getting a little dated because of COVID. You know, everyone was caring about exponential growth.
Oh yeah, the heart one was kind of cute.
Yeah,
Oh yeah, that was around Valentine's Day.
yeah. The problem is, it's like, even if I saw y'all on Valentine's Day, I wouldn't see my other class on Valentine's Day, so it's hard to...
Yeah, but around then is fine.
Mr. Johnson, can I take the ball pass and go over and get some water before class?
Let's wait.
Okay.
After you finish your mini quiz.
Gotcha.
I was actually about to put one of these back up, and then...
I always like a good fun.
Yeah.
Those are the ones where they take something from real life into calculus context. Like the aspirin one.
Oh my god, I get it now. I forgot what the sun thing was for, I think, when that one actually came out.
Yeah, that one's pretty good, too.
That one was pretty good.
No, I like the you with that glasses one.
Glasses?
Yeah, it was more recent, I think.
Elementary math. I just like that meme in general. Your math has numbers? What the heck's a
Unfortunately,
number?
that's kind of true. A little bit.
No, it's like, I think I did worse on the ACT this year than I have on any previous year because I forgot how to do all of the math with numbers. Because I haven't had to.
Yeah, you got to review. This is the best one that someone's ever sent me. A student sent me that one last year.
Yeah, that one's a good one.
But I like cats, so that's pretty good. If you know the definition of pi. That one's pretty good. If you like Mario Kart.
I thought it was good. But if you put me against like anything that isn't a computer, I realize that I am not good at Mario Kart.
I like this one too. I don't know why. That guy looks like one of my
It's
friends.
kind of a cliche one, but it's always good. Oh my god. It's such a mood.
Intermediate value theorem doesn't get a lot of love, so that one's pretty good. Okay, our bells are turned off. They'll be turned off the rest of this week and next week because some of the AP testing is on campus. So we need to go ahead and start so that you guys can get in some studying and some review today. But first off, we've got a 2-question mini quiz. So if you go ahead and put your stuff to the side for that. This is obviously the last mini, well, I guess it's not obvious, but I'm not going to give you a mini quiz tomorrow because you guys had one extra day before the AP exam than my A-Day class. So
Do you have any work planned for after the AP test?
we'll do a couple small things, but it's nothing major, nothing to worry about. It'll all be stuff that would be no homework and probably take less than half of the class.
The chemistry teacher assigned an entire group research presentation. It's all. It's not that bad, but it's all. You know.
Well, if I find out y'all are snoring during the AP test, I will change my mind and give you lots of work, so. I think I've warned you of that before. What's your breakfast? Peanut butter and peanut butter?
Second breakfast I had, avocado, tomatoes, some eggs on it this morning. Milk, Jim's.
You can take this one tomorrow. So let's worry about this first. There is a Google survey I'd like you to do. It is about, I don't know, 5 or 6 questions, very quick, just about how you feel about the AP exam and stuff. Basically the information that I shared with you from last year's group, as well as give you some input for next year's group and me on just, well, you'll see when you pull it up. But if you finish the mini quiz quicker and you're waiting for everybody else, you could go ahead and do the Google survey. And if you didn't finish the circuit last class, which I think you all did, but if you didn't, I ask that you finish that up so I can give you a grade on that as well. Then I've got a video I'd like to show you. So first time I think I've shown you a video all year. And then I'll discuss the 2 handouts that you picked up. Whitney should be here. Mike Oliver. Matt should be here. Anthony. Thompson.
Am I able to take the part 1 of the...
Are you done with this one?
Yes.
Part 1 of...
The 10 points closer quiz.
Oh, okay, yes. This class.
Thank you.
A lot at the end of the class here. Their final was
Class.
finite. Friday now.
Yeah. But I wasn't excited with the same base for once.
It's like integrating.
On the right side, I get to see.
I get the same base. Always instructs.
What's your binder?
No, I like how it's very much.
But I can't. I can never.
Started.
I can almost.
One time I got the, when I was dosed up, and I get sick, I dropped like 2
Okay, if you're still working, that's fine. Go ahead and keep going. You can get an 80-inch bench. But those of you that are done, if y'all would go ahead and pull up that Google survey real quick, please.
If you can't read that link, let me know. I guess while you pull that up, I'll talk about the 2 handouts you guys picked up so that you know what to look for in those. So one of them is 143, 10-point closer part 5. So this is the last part of it. So there's certainly a bunch of other stuff I was trying to get on there. But again, those handouts, I wasn't trying to give you a packet that says like, here's everything, learn it all. I was trying to pick it out where I could expect at least 10 points from each of those 4 to 6 skills on each one of those I handed out to you. So if you work through that one, that should get you another 10 points. And if you work through all 5 of those, you should be at 50 points and feeling pretty comfortable and less stressed about the AP exam. So I'd like you to work through that today. I think there's only 4 on this one. But then 144 is what I call the AP Survival Guide. So it's just got some information on there. I don't have mine in front of me, I don't think. But some of that stuff is some good information, and some of it's stuff I haven't bugged you about to death, like other things. So it talks about stuff you should do before the AP exam and basketball. So like maybe the night or 2 before, some stuff like if you're going to bring your own calculator, you need to make sure it's in Radian mode. If you're going to borrow a calculator when you're at the AP exam, one of the first things you need to think about is putting it in Radian mode, because it may not be. You know, everything we do in calculus is in radians, so you know you're going to be getting some answers, not understanding why your stuff's not working out, wasting time, and then even if you're fortunate enough to remember what it was, you might have shot yourself in the foot. And again, that's just one thing, you know. So I wanted to put all that in one typed up place so that you had something to look over the night or 2 before the AP exam. I know on the back page it also gives you some study ideas and the things that I would prioritize. So I remember I put down first, if you feel like you need to study, I would stick with these 10-point closer handouts first. I think that they're probably the most important. Again, they're not random skills, they're skills that I know that they ask about. Second would be the 2 FRQ types we were told are on all AP exams and where you could find some practice ones. And then the 3 other types that are common enough that they get asked almost every single year too. So you can read that, get a reminder where it is. I think number 4 says, like, make sure you know all the basics you're supposed to have memorized, like the quotient rule, the product rule, knowing where there's minus signs and plus signs and derivative of trig functions and all that kind of stuff. And I attached those to the last 2 pages. So there's not like any questions to work out on any of this. It's just a reference. I'd make sure that I knew those. And then I list a bunch of other things depending on what your style of studying is. So things from like, I have 2 optional mock exams open in AP Classroom. If you like that, I remind you that you could go through Khan Academy and try their test, quizzes, videos, whatever. There's AP Live videos that you could watch. There's all kinds of stuff, but that's on the back of the front page. So if you're looking for some more ideas to study, I throw out some ideas that I think would be useful for most people. The 3rd page, I think, has the units broken down and their percentage weight on the AP exam, in case you're interested. I know the front page has the testing schedule, like what section's first, what section's second, in case that's important for you to know beforehand. And then I think the last couple pages are just those reference pages, things you're supposed to have memorized. So obviously you should probably be able to go through and just check those off. But if there's some of them that you're kind of shaky on, or if sometimes you forget the minus sign in the quotient rule or whatever, then leave them unchecked, and you can check them off when you look it over the night or 2 or morning before your AP exam. So just try to give you one document that can kind of help push you in the right direction when you get there. And of course you're welcome to look at that during class too. Okay, the other thing I'd like before I let you work on that, because I know everybody's at a little different place there. Oh, I lost it. Gotta find it. All right, so unfortunately for y'all, I have been lying to you all year about calculus. And you did not need a full year to learn calculus. You needed one 20-minute video. So this video, which again I have not shown you any video all this year or last year if you were in my pre-cal class, but I like you to watch this one because it's a little bit silly. And this guy, Professor Berger, tries to go through all of calculus in under 20 minutes, and so it's pretty intense. But it makes sense for us to look at it as we get right before your AP exam, because if he's summarizing calculus in 20 minutes, if something comes up that doesn't sound familiar to you, then that might be something that you don't know about that you're supposed to know about. And again, it's lighthearted and just kind of silly, so you don't have to take notes or anything. Just follow along and see how well he can do.
Alright, so now we're going to try to do the impossible. We're going to try to do all of calculus in under 20 minutes. We have to run really, really fast, go through the whole course. Let's begin. The first 2 basic issues of calculus, 2 big questions, what are they? How do you find instantaneous rate of change? How do you find how things are changing instantly? And then, completely separate from that, how do you find areas under curves? 2 completely different questions. Turns out answers are completely related. Let's see how they go. Question 1, instantaneous rate of change. What are we going to do? Well, what you do there is you first remember, what does rate mean? Well, rate is just change in distance over change in time. It's as easy as that. Distance equals rate times time. Not a big deal. Okay, now what do you do with that? Well, if you graph a function that represents sort of distance against time, then what do you notice? If you want to look at the change in time and the change in distance, what do you got? You actually got a slope of a line. Right? This is slope, rise over run. Change in distance over change in time. Distance over time. So you got a slope. So automatically we see a really neat thing. We see that the average rate of change between 2 points is equal to the slope of the line connecting them. Well, that's really cool. By the way, what about lines? Maybe you forgot about lines. I'm going to remind you about lines. Okay, no problem. We can do lines. We can do lines. Lines. Y minus y1 equals m times x minus x1. This is the point slope form. All you need to give me is a point on the line, x1, y1, and a slope, m. Give me those 2 pieces of information, I can always write down the line equally. Always, always, always. Never forget it. Okay, fine. So now we're back here. Now we can find average rate. And what do we see? Well, in fact, a line that touches the curve at 2 points is sometimes called a secant line. So in fact, we just discovered that the average rate, change in distance over change in time, is equal to the slope of the secant line. Cool! So all you have to do, when you want to find average rate, connect the 2 points with the line, find the slope, you got the average rate. No biggie. But that's not what we want. We want instantaneous rate. So how do you do that? Well, what would that be? Well, if I want to find instantaneous rate here, what would I do? I make that secant line closer and closer and closer, bring these points together, and look what I'm converging to. I'm coming to a tangent line. Wow! Instantaneous rate of change equals the slope of the tangent line. So we want a slope of the tangent line. Well, what's the slope of the tangent line? It's change in y over change in x, change in distance over change in time. But now the change in time from that point to itself is 0. 0 over 0. So I'm getting 0 over 0, which is complete garbage, and that is a big problem. Our first major problem of the course. Okay, so what do? Well, we can that. Distance equals rate times time. We're going to can that. It says rate of change. I really want that. So what do? Well, how do we get that 0 over 0 problem to go away? The answer is we inch up to it. We just approach the 0 point. And what would that look like? Well, let me remind you what you've done when you were a little teeny kid. When you were a little teeny kid, this is what you're looking at. You're looking at a value of function at a point. Value of function at a point. Okay, not a big deal. There it is. F of A, it's that point. But you don't know anything else about the function. You don't know what's going around there. So all you're looking at is F of A. You open it up. Woohoo! Function will be quite interesting. Who knows? Okay, but now what I invite us to do, and what calculus invites us to do, is to look at the function this way. Cover up that point and look at everything else. Open the window, look outside. That's where calculus is. And what you see here is we can see what things are approaching, and we can actually determine the idea of a limit. The limit is what things are approaching. We don't care about what actually happens at that point, only what things are approaching. Armed with the idea of a limit, what can we do? Well, now we can return to the question and figure out, let's take the limit as delta t goes to 0. What do we get? We get 0 over 0. That is called an indeterminate form when you get 0 over 0. So what do? You gotta do some algebraic gymnastics. You gotta factor the top and cancel with the bottom. You can try to multiply by the conjugate. You can try to combine the fractions. There's all these tricks in the trade to actually reduce this to something that you can actually find. Find the limit. Okay, but once you find the limit, and you take the limit as delta t goes to 0, what do you get? You get the answer to the question, how do you find instantaneous rate of change? The answer is what we call the derivative. And what's the derivative? It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Looks pretty confusing, doesn't it? It's just rate. It's distance over time, but now I'm letting the time go to 0. Not a big deal. So that's the derivative. Bingo. We're done with the first question. And so now what do we see? Well, we see now that we come back here, and the derivative, in fact, gives us the slope of the tangent line. Well, that's really cool. If you want to find the slope of a tangent line ever in life, you just take the derivative, and that gives you the slope of the tangent once you evaluate it at the point you want. Great. But for free, we answer the first question. Because remember, the derivative also represents the instantaneous rate of change. So you want to find out how things are changing? No big deal. You take a derivative, plug in, and that will tell you how things are changing at that instant. Okay, great. So now we know all about how to graph these things, how to look at these things. The derivative is same velocity. Boom, boom, boom. We got all out of the way. Now let's take a look at some applications. What can we do with this? Well, how would you take derivatives of complicated functions? Well, if you got a product, you have the product rule. Remember the product rule? Don't memorize the formula, memorize the chant. First times the derivative of the second, plus the second times the derivative of the first. So the derivative of a product is this. It's not the product of derivatives. You got to use the product rule. We've got 5 minutes to figure out, okay, folks, I got to move faster. What if you have a quotient? Well, then use the quotient rule. And what's the quotient rule say? If you got a quotient, you take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's the quotient rule. That's what you use when you have a derivative of a quotient. Okay, great, no problem. Now, what about if you have a really complicated function? What if you got a function that looks like this? It's got insides. It's got guts right in there. So you've got something like this, and you want to take the derivative of that. What do you do? Well, you got to use the chain rule, folks. This is a thing that you can chain together. There's an inside, there's a block right here, there's a whole big block there, and then you've got an outside. So take the derivative of the outside. The derivative of sine of block is actually cosine of block. So it's cosine of block, and what's the block? The block is going to be 3x cubed plus 1, and then you multiply that by the derivative of the inside, and the derivative of that turns out to be just, let's see, 9x squared plus 0. And so there's the derivative using the chain rule. The idea is to peel off like an onion. Just peel off, keep peeling off the outside until you get to the inside. Always remember though, when you take the derivative, it's if you have sine of block, the derivative is cosine of a block. Don't put the derivative in there, put the block and multiply by the derivative of the inside. That's the key to the chain rule. Now we got the chain rule. Okay, but what about when you have functions that aren't functions? Like what if you have things that are relations? Like x squared plus y squared equals 1, like a circle. How do you differentiate that? How do you find dy dx there? Well, the answer is we use something called implicit differentiation. Implicit differentiation, how does that work? Well, you've got to remember that dy dx, that's an object, that's a noun. And d dx is a verb, it's a commandment. Take the derivative with respect to x. So you differentiate this with respect to x, and what do you see? Well, you see something just like this. What you do is, you say, okay, I'll take d dx of x squared plus y squared equals 1. The derivative of x squared with respect to x is just 2x, not a big deal. The derivative of y squared, remember how I think about this? I think about this as clumping all this together. And I see this as a blob squared, so I actually use a chain rule, which we just developed. And the chain rule says the derivative of blob squared is 2 blob, and I multiply that by the derivative of blob, which is the derivative of y with respect to x. That's called dy dx, folks. The derivative of 1 is 0. And now you can actually solve this for dy dx by bringing this to the other side. That'd be a minus 2x. You divide by the 2y, and you see dy dx equals minus x over y. And there's the answer. So that's implicit differentiation. Just go right through and differentiate implicitly. When you have a relationship, you can still find the derivative. Great! We're making progress here, folks. We are cutting through this stuff. Well, now that you have derivatives, what can you do with that? Well, if you think about it as a velocity, you get instantaneous velocity. If you take the derivative of velocity, you actually get the change in velocity, which is acceleration. So we get acceleration now, we get velocity. Acceleration is just the second derivative of the position. So we can actually take derivatives upon derivatives upon derivatives, as many derivatives as you want. So it's great, we can do that. So higher order derivatives, no problem. What can you use these things for? Okay, we know it's true for velocity. We can use it for velocity. What else can we use it for? Well, it turns out you can use it for linear approximation. Suppose you've got some wacko function. You got some wacko function like this, woo, and you actually want to figure out the value right here, and you don't know what that value is. But you know nearby there's a point that you can actually compute. So what do? You find the tangent line approximation because you remember the tangent line closely emulates the activity of the function. Tangent line closely emulates the activity of what the function is doing, so they look the same there. So you find the equation of the tangent line, and then plug in the mysterious point, then you're all set, because you can approximate the value by plugging into the tangent line. So how would that look? Well, that's called linear approximation. Here's the formula, but don't bother memorizing it, just think about it. What you got to do is you got to find the equation of the line that's tangent at the known point, which is x here in this case, and this is going to be x plus delta x, the known point plus a little t offset, so you approximately equal to the derivative times the change in x times the function, plus the function. So that's it. That's the whole thing right there. Linear approximation allows you to actually compute things. Computers actually work this way. Computers know calculus. Everyone knows calculus. You've got to know calculus. Okay, now, what else can you do? Well, suppose that a derivative were to be 0. Well, how could that possibly happen? That could possibly happen because maybe the function goes like this, and I see the tangent over here has slope 0. Or maybe the function goes like this, and I see the tangent has slope 0. In particular, if the tangent equals 0, maybe we have a max or min. Also, maybe the slope or the tangent doesn't exist. Like if you have a wave kind of thing, a cusp, very pretty cusp like the waves. Well, that might be a max, that might be a min. So in particular, you can find out when objects are maximized or minimized. You can find the maxima or the minima very easily by using calculus. What do? You take a derivative and you see where it equals 0, or where the derivative doesn't exist, but the function does. Those give you candidates for possible max and min. And what can you use that for? Well, you can do all sorts of max and min problems. You want to maximize profits, you want to minimize costs. You go, oh my God, 20 minutes? No. It's only 10 minutes left. They're trying to fool me here, folks. I'm not going to go up for it. 10 minutes are left. Okay, so you want to maximize cost, you want to minimize cost, you want to maximize profit, you want to maximize area, you want to minimize volume, whatever it is, set up the problem really carefully, figure out exactly what you want to optimize, take the derivative, set it equal to 0, solve, find out where the derivative is undefined, and you've got it made. Really not a big deal. However, you should always remember and never forget the fundamental method of solving problems. So remember how you solve all of life's problems. The first thing you have to do is understand what you're being asked. You can't answer a question that you don't understand. The next thing you do after you understand what you're supposed to find, what you're being asked, is figure out what you know. List every single thing that you know, every single fact. Maybe it's superfluous, maybe you don't use it, who cares? Write it down, understand it, make it your own. And then the last thing is, take the information that you know and see a relationship between that and the thing that you see. Try to find a connection. Once you got the connection, then you're on the road to actually find the solution. That is the simple method for finding any single answer to any single problem. Another application, if we think about derivative as a rate, is looking at related rates. Suppose, for example, that you actually have a ladder, for example, that's falling down. The ladder is falling, and you don't want to be sued, but the only thing you do know is how fast the bottom is falling, you want to know how fast the top is falling. What you need to do there is, if you know this rate, you can find that rate by linking them up with a connection. In this case, the connection would be the Pythagorean theorem. You can take the derivative with respect to time, because here you see the variable, the thing that's independent that's always changing is time. Time keeps on ticking into the future. So you keep going like this, you actually solve this, take the derivative using implicit differentiation, differentiate with respect to time, and plug in what you know how this is changing, and that tells you how this is changing. Pretty cool. That's called implicit, that's called related rates. Suppose, for example, you drop a stone into a very, very still pool. You have a ripple effect. Those make concentric circles that are getting larger. If you know how fast the radius is changing, you can find how fast the area is changing because you have a connection between area and rate. Area equals pi r squared. So there you go, related rates. If you know how one rate is changing, you can find out how a related rate is changing. Okay, what else can you use a derivative for? Well, the other thing you can do is actually graph really, really accurate pictures of functions. Finally, you can figure out that a parabola looks really pretty and bowl-like, like this. And it's not something really exotic, but it's just a nice pretty bowl. How do you do it? Well, you just start taking derivatives and analyzing things. First, you find the critical points. Those are points where the derivative either equals 0 or the derivative is undefined, but the function is defined. So for example, in these examples right here, you'll notice that the derivative equals 0 here, the tangent is horizontal right there, the tangent is horizontal here. In this example, the tangent is horizontal here. And then where does the derivative not exist? The derivative doesn't exist here. The derivative doesn't exist there. Those are candidates for maximum. Those are called critical points. Then what do you do with those things? Well, you set them up on a little number line on the x-axis, and you look at the intervals all around it, and you see whether the derivative is positive or negative. If the derivative is positive, that means slopes are positive, so the function must be increasing. If the derivative is negative, then that means the function must be decreasing. So you can see that the function, for example, here is decreasing, 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 then increasing. Here you can see it's increasing, 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 then decreasing, then increasing. So you can see where it's going up and where it's going down by the sign of the first derivative. That also determines whether you have maxes or mins anywhere, and that's called the first derivative test. Now, how do you figure out the curvature? The curvature is given by the rate of change of the derivative, how the derivative is changing. So what you do there is you take the derivative of the derivative. So you look at the second derivative, and then when the second derivative is 0, are potential points of inflection, points where the concavity changes. This is concave up, it's curving upward. This is concave down, this is concave up. So the cup is sitting up, the cup is sitting down, concave down. So here you would see the second derivative is positive, then the second derivative is negative, it changes here. Now it's sitting up, it's positive, positive, or concave up. Here we're concave up, second derivative is positive. Now here we see it's concave down, second derivative is negative, and second derivative here is also negative. This is a cusp point, the derivative doesn't exist there. This is a point of inflection, this is a point of inflection, this is a point of inflection, and that's a minimum. So just by taking derivative and then second derivatives, you can actually figure out and graph a very accurate sketch of even very complicated, almost scary looking functions. By the way, if you got fractional exponents, expect cusps. That's my word of warning of the day. Okay, now, if you've got really exotic functions that have denominators, then actually you may have asymptotes. So don't forget that a vertical asymptote is where the function, after you simplify it, the bottom equals 0. So wherever the bottom equals 0, after you simplify and reduce, those are going to give you your vertical asymptotes. Horizontal asymptotes, you take the limit as x goes off to infinity, as you go up to the horizon, and you see what y value you're trying to land to. If you're landing somewhere, then you know you've got a horizontal asymptote, and then y equals that value. So you put in the asymptotes, and then you can do all the other calculus, get the curvature, see exactly what the beautiful picture looks like. And that was the end of the differential calculus. Great, no problem. Now what? Well, now we move on and look at the exact same thing we just did backwards. So we look at Math Jeopardy. Oh my goodness, I have only 5 minutes left. So Math Jeopardy, here we go. So the idea is, if I tell you what the derivative is, how can you find the function whose derivative is that? Well, this is the notion of an antiderivative. So how do you actually find antiderivatives? Well, we put a formulas for that. If you want to find the antiderivative of x to the n, it would be x to the n plus 1 divided by n plus 1. Take the derivative of that to see you get x to the n. Unless n equals negative 1, then you're looking at the integral of 1 over x. And what's the integral of 1 over x? Well, it's the natural log of the absolute value of x, because the derivative of natural log we already saw was 1 over x. So great. Now, how can you find exotic integrals? Well, remember that d dx represents differentiating with respect to x, and so therefore the integral with respect to x represents to integrate with respect to x. Now, if you have a very complicated thing there, with an inside and outside, you might be able to untangle that, which potentially was made by the chain rule, by using substitution. Let u equal some big block, and the big block's derivative should appear somewhere else in your integral. If you've got that, it sounds like a good candidate for u du substitution, and then you've got to change the dx to du by taking derivatives and seeing what du equals in terms of dx. So that's the u du substitution. You got that going on here. And now what you can do, you can take that and look at studies of motion again. Now I can give you acceleration. If you integrate, you get velocity. If you integrate again, you get position. So vertical motion, not a big deal anymore. Lands, no problem. Things moving in space. Like this thing here, watch it folks. Woo! You can get that. You can anything that moves, anything at all that moves, we can now analyze whether you have crabs or whether you have a bike. It's not a problem anymore, folks. If it's movement, we can anti-differentiate it and figure out what it is. Not a problem. Now, where does this lead us? Well, it brings us back to the very first question of the course, which was how do you find areas under curves? We have to answer that. We haven't done it yet. It turns out the surprising answer is that it's the fundamental theorem of calculus. And the idea is if you want to find the area under this curve from A to B, right here, you want to find that area, then how do you do it? It turns out that if that function is called, let's say, f of x, then all you do is integrate from a to b f of x dx. Because you're summing up little rectangles in here that are base, small change in x, base times height, which is the function you go from a to b, and this equals f of capital F of b minus capital F of a, where what's capital F? That's the antiderivative. So if you take the derivative of capital F, you actually get little f of x. So just find the antiderivative, plug in the big point, plug in the small point, subtract, that will always give you the area under the curve. You can look at the areas of more exotic things. For example, if the thing actually goes like this, then actually, this is actually not very x-easy. The rectangles aren't very clear. The rectangles change from going from green to green, over to green to orange, and to orange to orange. It's not very uniform. However, if you put the rectangles in this way, and stack them this way, now you're summing with respect to y. And so here you would actually sum this with respect to y, so you would integrate this, dy, and put the rectangles in this way, then you put the rectangles in that way, and stack. You stack from low to high, and you stack the rectangles like this. Okay, that is all of calculus. I did it in under 20 minutes. That's what it is. Go back, think about it, have fun with it. Congratulations, folks. You just finished Calculus 1. Have a good time, celebrate. Good luck in the final. Bye.
So what do you think? Could we have just done the video
I
and
think we should have done that. Start of the year and then just party for the rest of the year.
you would remember all of that at the end of the year?
No, we should have done a review. Like right now.
That's something you don't do.
That's actually so helpful though.
Oh, well,
Anyway, it's kind of
That
silly,
sounds
but it
fun.
also does kind
he
of
also didn't touch on my
formulate, summarize everything we talked about. So I feel like it's a good use of 20 minutes. Okay, so again, the surrogate from last class, if y'all did not finish that up, if you've got some time to finish that up, I'd like to give you homework points for it, so as long as you give it to me sometime today, unless you were absent last class, you obviously have a little more time. And then I'll give it back to you in case it's one of those things you want to look at. And then you probably should start working through the 143, make sure that you're comfortable with those skills or start practicing some of those skills. Might be worth a few minutes in class to scan through the survival guide thing just to see what is there. It is a B week, so I will see you guys again tomorrow. And again, I don't have more review stuff. I tried to put everything that I thought you might want to use on that survival guide. You know, at this point, it's really up to y'all how much more effort you want to put into it and how much studying you think you need to do to be sure you pass. So one other thing to keep in mind too is this Sunday is Mother's Day, so if you were planning on studying all day Sunday, you might need to take that into account. But of course, if you guys have any math questions I can help with, I would be happy to help you. But honestly, you're probably all working on different things, so it would be easier to just help you individually. So make sure I get the 140 circuit today, and just use your time to study for your test, please. 140 was the circuit on Riemann sums from last class. Should be 2 pages. And I didn't ask you to turn it in for homework, and it's not open in Google Classroom or anything like that. It's just, again, I'm pretty sure you guys finished it in class last time if you were here, so I just wanted to give you a few points. And again, I will give that back to you just in case it's one that you need to study. I don't want to keep it from you. Also, if you're missing any other of your handouts, maybe something you turned in physically at some point and you never picked it up, I've put return papers, not tests and stuff, but return papers in that white box over there where you put your phones during test. And one of the trays is specifically for your class. So if you're missing something and you think that I have it, it's probably in there. and you're welcome to go through there and get anything with your name on it. I guess I should also remind you, I feel like you should be done with the Delta math corrections, but I also told you I really didn't care when you did those as long as it was done before the AP exam. So if you've just been busy and not been able to do that, make sure that you have that in before Monday. This 140? Yes. I have no interest and will not get any extra points for doing the Delta math after the AP. Point is to do it before to help from your mistakes. Also, this should be irrelevant and not even on your radar, but next Tuesday, the day after the AP exam, I will not be here. I'm not skipping or anything, but there is a training thing that they're asking most of the math teachers to do next Tuesday. So I will be across town. I will still be at work, but I won't be in here. So you don't need to worry about me. I don't want to say anything specific about the mini quiz today because there's still a couple people that need to make it up, but there was a little bit of a trick to the first question if you were paying attention. So if you don't know what I'm talking about, you might bring yours up to me and let me give you that hint. You actually showed some work.
Hey.
I did? Yeah, it took you all year, but. Just put it in the bucket. Yep.
If you go through the entire chemistry class, I guarantee you it's faster to just do this again.
On this one, what does that equal to?
I did that.
Okay, that's fine.
Yeah, I didn't use that definition of the derivative, but I wanted to prove my thought.
Gotcha. I'm just making sure that you realize that you could have gone straight from here to here if you were thinking about the trick part of it. Yeah, you got that one. Oh, and you did it up there. I didn't realize that. Right here, though, you need to be careful. You can't cancel out terms like that. Y'all had any difficult AP exams yet? No?
I would take one. Yeah, for next week.
Can, like the MCQs are like, not the best for me, very hard stuff to do. And then FRQs were like super.
Oh, yeah.
You don't consider your chemistry test to be a tough one?
No.
It wasn't as super hard.
It was easier than some of the later tests that we took
The
in class.
Yeah, the FRQs, those are the easiest FRQs I've taken.
I'm glad you could.
Which is probably a bad
What's
sign for
this
scores,
equal to?
because if you miss like 2, you're dropping 3
Oh, that?
numbers.
What's this over this?
That's what it's equal.
But
What is it?
You only did this
Oh,
5,000 times.
tangent.
Okay. What's the derivative of tangent? Mm-mm. No. You need to memorize your creek derivatives again.
This, just basic.
Yeah, so you just derived it.
Okay.
Whereas I would suggest you just memorize it so you don't actually have to do that on the quiz. I'm glad, what I'm saying, I'm glad you can do
Yeah.
that, but there was a